All right, so in this last section, we're going to look at spatial interpolation. So going from discrete measurements to a space-filling surface using different methods. We're going to start off with the discussion of density estimation, which is a bit of a review, and then we're going to talk about some fairly simplistic interpolation methods, including inverse distance weighting and spline, and then we'll end with a discussion of Kriging. Okay, so here's a review of density estimation. Here we're going to look at point density, line density, and kernel density. Okay, so point and line density. So the idea here is to calculate the magnitude per unit area for point or line features that fall within a neighborhood around each cell. So the idea is that you create a window that's user-defined shape and size. It counts the number of features, either number of points or length of lines that fall within that window around that cell, and then stores that information on the pixel, moves on to the next pixel, and does the same thing. So effectively, this is another example of how we use moving window analysis to create output in GIS, and specifically with raster data. The output will be line length per area for line data and number of points per area for point data. Note that it's also possible to incorporate weights. So, for example, if you had points that represent houses, you could weight them based on the number of people that live in that house or structure. Again, to do this, you must specify neighborhood shape and size. Generally, the larger the neighborhood, the more generalized the pattern will be, and the smaller the neighborhood, the more localized the pattern will be. Again, there's not really a right answer in terms of what the right window size or shape is. It really comes down to the type of question you're interested in and the type of patterns you're interested in exploring. I would suggest just experimenting with different shapes and sizes and how that impacts the output. In this image here, basically darker areas of purple indicate a greater density, and then lighter areas indicate a lower density. And again, this would be impacted by changing the size and shape. Okay, so moving on from there, what I tend to not use those methods that often. Instead, I generally use kernel density methods because I find they're a little bit more robust and useful. From the last section, we talked about kernel density graphs in which we plot the density of features relative to a specific variable. So this is kind of like in one-dimensional space. Again, if we extrapolate that into a two-dimensional space or map space, we end up with basically the same surface, but again, two-dimensional. So you kind of imagine these as, instead of being color-coded, as kind of like raised bumps, similar to these density curves over the map space. This image here is specifically showing the density of man-made structures across this region. So you can see the concentration around cities. This is Morgantown and Fairmont and Grafton and Kingwood, for example. So this sounds a lot like point density, right? But it's actually implemented a little bit differently, and that's because it makes use of a kernel function to estimate density instead of just counting the number of points that fall within a window and dividing by the area. So what does that actually mean? So here's a slide with a lot of text that tries to summarize the difference between point and line density versus kernel density. So in point and line density, a neighborhood is specified that calculates the density of a population around each output cell. So you define a window, it's a moving window analysis. You calculate the number of points or the length of lines within that window and divide by the area of the window, store that on the cell, move on to the next cell. In contrast, kernel density spreads the known quantity of the population for each point out from the point location. So the resulting surface surrounding each point is a kernel density based on a quadratic formula with the highest value at the center of the surface, the point location, or the cell location, and tapering to zero at the search radius distance. For each output cell, the total number of accumulated intersections of the individual spread surfaces is calculated. So the idea here is that instead of just allowing that density to spread evenly over the moving window, that density is concentrated close to the middle of the window or close to the cell that's being calculated, and that density curve tapers to zero on the margin of the moving window. Because you're going to have overlapping moving windows, you have to sum up those densities that overlap to get the final density on the cell. So again, it's basically concentrating the density close to the center of the window over the cell that's being estimated, instead of it being uniformly distributed over the cell, over the moving window as it is for point or line density. I think this is, generally speaking, it depends on what you're interested in, but I do feel that this seems to be a more realistic estimation of density, so I tend to use these methods as opposed to point and line density. Okay, so after that review, now we're going to move on and talk about spatial interpolation methods. And we're going to start off with the simpler methods. Okay, so what is spatial interpolation? So it basically is trying to predict a value at a location where you do not have a value. Here's kind of a surrogate in graph space. So this is not spatial. So imagine we're trying to predict y with x, and these are the measurements that we have. So the model that we use to try to predict y with x is a line in this case, so it's regression like we talked about in the last section. So if you were trying to predict a new y within this range where you have data points, that would be an example of interpolation, because you're predicting within the graph extent of the data that you have. In contrast to that, extrapolation is when you're generally predicting outside of your data bounds, so higher or lower values of x to predict y. Generally, it's considered to be safer to try to do interpolation as opposed to extrapolation, because we have some more controls here. So for example, we're assuming this is a line, but maybe as values of x decrease, this trend actually tapers off, or maybe it dives, maybe it tapers off up here, or increases, or the slope increases. So we don't really have controls in that situation. So in both cases, we're still guessing. It's just generally considered that interpolation is a safer bet or a better guess than extrapolation would be. So moving into the more spatial domain, we can think about interpolation as trying to predict a value within the geographic bounds or spatial extent of where we have data. So imagine that all these red dots represent measurements. So maybe they're gauging stations for weather. Maybe there's where soil bores were collected. So if we were trying to estimate the value of this location from these measurements, that would be spatial interpolation because it's within the geographic bounds of the data. Whereas trying to estimate this value way out here, that would be spatial extrapolation because we're outside the data bounds. No matter what you do in this situation, there's still going to be some error, because you're trying to make an estimate or a guess of a value where you haven't actually collected that information. So in short, we generally try to interpolate as opposed to extrapolate, but we always recognize that going from discrete measurements to a space-filling surface is always going to induce is an estimate, and thus will be some error. Okay, so one simple method that we already talked about that falls under the umbrella of interpolation is Thiessen or Voronoi polygons. We talked about this already. Effectively, the idea here is that it defines the area that is closer to one point than any others in a data set. So, for example, all these points represent weather stations across, I guess this is Ontario. So every area that's within this polygon is closer to that gauging station or that weather station than any of these other mapped weather stations. Same thing for this area, so on and so forth. So you can see areas where there are denser measurements, you have smaller polygons. Areas where they're more spread out, you obviously have larger polygons. So effectively, why this is an interpolation method is that you're going from discrete measurements, these point locations, to a space-filling surface, to a value or estimate everywhere, and specifically every location is going to get the value that is associated with the nearest, in this case, weather station. So discrete to a continuous surface. This is another example. So these are major cities in West Virginia, and these bounding areas indicate regions that are closer to one city than any other. So for example, this is Clarksburg, so all of this area is closer to Clarksburg than any other city. This is closer to Fairmont, closer to Morgantown, closer to Beckley, closer to Charleston, so on and so forth. This may seem fairly simplistic, but note that this is actually used. So for example, this has been used pretty consistently to try to interpolate, say, ground measurements from weather stations into a space-filling surface. This is the method, for example, that's used by the Voronoi experimental forest here in West Virginia to create space-filling surfaces from their ground station weather measurements. Okay, so moving on to a new technique, we're now going to look at inverse distance weighting, or IDW. So, again, stands for inverse distance weighting. So effectively, this is an inverse distance weighted average of near sample features. So what does inverse distance mean? Effectively, what that means is that it's weighted by the points are weighted by the average of by the inverse of their distance. So you get an average not from a straight numeric average where you just take the nearest points, sum them up, divide by the number of samples. The near ones are actually being weighted higher in the calculation. So near points are weighted higher than points that are further away. And the reason why we do that is we assume that near points are probably going to have more similar values than further points, so we want those to have a bigger impact in the calculation or model. When you run inverse distance weighting, there's a couple different settings that can impact the output and the prediction. So one is the power. So this controls the significance of surrounding points. So you can think of this as like powers like on a polynomial. So higher power equals less influence by distance, and lower power equals more influence by distance. So the higher the power, the more weight the near points will have, and the lower weight the distance points will have. The lower the power, it means that further points will have a higher weight than they would have with a higher power. So how do you know what to use? Again, that's not always clear. I generally, honestly, just use the default settings unless I have a reason to use something different. But you can experiment with that. If you really want to have near features be weighted high, then that would mean setting a higher power value. The other setting you can that can be defined is the radius. So this specifies which input points will be considered. Generally, you don't want to use every single input point in the data set. You want to use a subset of near points for each new location that's being predicted. So if you set this to variable, you don't specify a distance but a number of points. So for example, you would say use the nearest 12 points or the nearest 7 points regardless of their distance. Note that you can specify the number of points to use, but you can also set out via maximum distance. So if you say 12 points, but there aren't 12 points within that defined distance, it'll just use the points within that defined distance. Another option for the radius is that you can use a fixed radius. So you specify a distance over which to search, and all the points that fall within that radius will be used. You can specify a minimum number of points that is used to increase the search radius. So for example, if you set a low search radius and for some areas there just aren't any points within that radius, then you can expand it out to incorporate some additional points. So for example, there's no points, but you set a minimum of 4, so that means that it's going to have to expand out to capture at least 4 nearest points. Again, there's really not hard rules about what good power and radius settings are. It's something you have to experiment with. It's kind of a case-specific issue. Note that inverse distance weighting is generally pretty good if you have fairly dense measurements and things don't change fairly drastically across the landscape. If the measurements are weirdly dispersed, clustered, for example, or there's lots of gaps, inverse distance weighting may not be the best option. Okay, so here's some examples of some outputs created using inverse distance weighting. So as you can see here, we have a very dense data set of bathymetric or water depth measurements here around New York and Manhattan Island and whatnot. So we want to take these discrete point measurements and turn those into a space-filling surface. And to do that, we used inverse distance weighting, and we ended up with this surface. The darker blues indicate deeper water, so you can kind of see the deeper water here and the channel going up into the bay. So here's how that was set up. So we had a set of point measurements. We used a field in the table that had obtained or contained the depth. Note that this should be something numeric or continuous. It generally doesn't make sense to use these methods on non-continuous data. We created a raster output because it's a continuous surface, can define a cell size, and these specify how the inverse distance weighting will be implemented. So here we're using a power of 2, a search radius of variable with a total of 12 nearest points, and we're not specifying a maximum distance. So in this case, it's going to use the 12 nearest points no matter what the maximum distance is. In this case, I'd argue that's fine because the points are fairly dense, so we shouldn't have a lot of gaps. You can also input barrier or polygon features. That would be if you know that there's a fairly drastic change, and that can be modeled as a line. So for example, like including a road cut line feature inside of a data set in order to interpolate an elevation surface. Okay, so the next method is Spline. Honestly, I don't use Spline much. I find that most of the interpolation problems that I run into are really not Spline is really just not applicable to those. So I don't use this that much. So basically, here's the idea. So imagine that the points extrude to the height of their magnitude. So whatever you're measuring. So if you're measuring elevation, they extrude to their elevation. If you're measuring depth to water table, they extrude to their depth. Spline then bends a sheet of rubber that passes through the input points while minimizing total curvature of the surface. So you're trying to basically create a smooth surface that passes through the points. So it fits a mathematical function to a specific number of near input points while passing through the sample points. So you're basically passing using a local window. You're kind of passing that. You're creating this kind of smooth surface. So the surface passes through the control points and then has to minimize the curvature of the surface. So it's as smooth or simplified as possible. This method is best for interpolating smooth surfaces that do not change abruptly. Again, if you got something that varies or could vary fairly drastically or fairly complex and is not modeled by a smooth mathematical surface, then Spline is not a great option. If you have a more subdued surface, maybe like the potentiometric surface for like water or for groundwater, maybe that would be more feasible or reasonable. Okay, so to end, we're going to talk a little bit about Kriging. This will not be a full-blown discussion of Kriging because that's honestly a fairly complicated topic. So instead, I'm just going to give you an introduction to Kriging. So if you take an advanced course, you'll know what it is and how it might be implemented. But the nuts and bolts of this are actually fairly complex. There's students who do like entire like theses or dissertations on Kriging. You could take a whole course on Kriging, and there's also different types of Kriging. So in many ways, Kriging is just a field and a study in and of itself. So we're just going to do a brief introduction here. So what is Kriging? So here's the idea. So spatial variability or change in values consists of two components. So a global trend and local spatial autocorrelation. So the fact that near values tend to be correlated with each other. So to create a Kriging surface, we make use of those two phenomena. So the global patterns and then local patterns. So we need a model of global trends. So that could be like a polynomial or a linear trend or something. And then we need to be able to model spatial covariance or spatial autocorrelation and incorporate that into the model. And that's done using geostatistical methods. Okay, so generally we start off by looking for global patterns in the data. So is the data approximated by like a polynomial surface? Is it approximated by a linear surface? What directions do the trends have? So for example, here we're seeing this is temperature data through Ontario. And as you can see here, temperature data tends to increase as you go south, decrease as you go north. So maybe some type of linear trend decreasing towards the north would be a nice global fit for the data. Again, many real patterns might be much more complicated than that. So we're using, again, some simple mathematical model to create a global trend over the data. Here's a different trend. This is ozone data in California. As you can see here, this is not linear. You're kind of seeing that the higher ozone values tend to be towards the middle of the state, both in the east to west direction and also in the north to south direction. So maybe a polynomial type surface would be the most, like with a second order, would be most useful in that situation as opposed to a linear trend. Okay, so here we have a linear pattern. This is for ozone data over California. So here we've fit a global function through the data where high values are towards the middle and it tapers towards low values at the side, as was suggested in that the spatial trend graph we just saw earlier. But obviously this is a very simplified representation of the true pattern in this data. And that's because all we've done at this point is try to assess or model a global trend. We haven't tried to actually assess or model any local trend or pattern. So the idea then is to improve this by to reduce the residuals or error in the model by modeling a local trend. And we do this by exploring the spatial dependency or spatial autocorrelation of the residuals. So we model spatial autocorrelation using a semivariogram first to get a sense of the patterns in the data. So things like the range, the sill, and any type of directional trends. This is a review. I don't know that we need to go over this again because I covered this in the last video, but one way that we can look at spatial autocorrelation is with the semivariogram. So again, semivariance is a measure of the spatial dependency between two points or features. It is the difference squared of the two values. So if there is no difference or they have the same value, semivariance is 0, and if they have very different values, then semivariance increases. We can model that or graphically using a semivariogram. So in a semivariogram, again, the x-axis represents the distance between 2 points or measurements, and the semivariance is a measure of basically how different they are. So near features tend to be more similar, so they have a low semivariance. Features that are further away tend to be more different, so they have a higher semivariance. Again, in this graph, the points, the red dots here, represent not one measurement, but a measurement pair. So their x-coordinate is the distance between those two measurements, and the semivariance is the square difference of the two values. So as you can see here, this eventually levels off. So this suggests that eventually the semivariance stops increasing. So it's as different as it's going to get. So let's move on to the next slide because there's more text there. Again, I already talked through this issue, but as a quick reminder, the range is the distance at which the semivariance stops increasing, or basically there is no longer like spatial autocorrelation impacting the data. The sill is the semivariance at the range. Again, at a zero lag distance or zero distance between points, you would expect to have a semivariance of 0 because they're the same location, but that's not always true. So, and we call that the nugget effect. If you subtract the nugget from the sill, we call that the partial sill. So why were we discussing this again? So the reason why we're discussing this again is because in Kriging, the semivariogram is used to get a sense of the distance at which spatial autocorrelation is impacting the data. And then if we incorporate that in, that allows us to model local trends and improve the global trend model. Okay, another issue is the concept of anisotropy. I can't say that word. So you might actually, if you look at the spatial dependency or the spatial autocorrelation in the data, you might actually find that it's direction dependent. And incorporating in that direction may actually further improve your model or allow you to further reduce the residuals. So you can incorporate this into Kriging model by exploring it in the semivariogram. So here we have a little window where we can specify the direction and the width of the values at which we're going to compare or produce a semivariogram from. And by setting that, we're able to maybe improve how this model fits the data and thus modeling our local trends to further augment the global trends. So in short, you can model local trends using the semivariogram and the concept of spatial autocorrelation, and you can also incorporate a directionality to it to further improve the model. Okay, so here are the general steps in Kriging. And again, we're oversimplifying this because this is a fairly complicated topic. I just wanted to introduce you to this idea. So the first thing is exploratory statistical analysis of the data. So are your data normally distributed? Are there directional trends? So on and so forth. Once you understand kind of the global trends, you can do semi-variogram modeling where you try to look at local patterns and the impact of spatial autocorrelation and whether there's any anisotropy or not. Then you can create a surface, and you can explore the variance over the surface in terms of error rates. So one thing that's complex about Kriging, it's not like most of the tools that we run in this class where you set it up and you run it and it's kind of like deterministic. Kriging is most appropriate when you know there's a spatial correlated distance or directional bias in the data, and you actually have to go through a process of trying to understand how best to model that and improve the surface. So here we can see that this is a much more complicated surface that is incorporated this more local trends over top of that global pattern that we saw earlier. There's basically a simple polynomial. So things to consider about your data. So is the data normally distributed? So you can look at histograms. So here this would tend to indicate that the data have a right tail or some outlier high values, so they may not be normally distributed. You can also look at QQ plots like we talked about last time. Here we can see a bit of an arc in the data, which might indicate again that the data are not completely normally distributed. You can also look at skewness and kurtosis values. See, they're reported here in this graph. And these tools are generally available in most GIS software packages like ArcGIS Pro, for example. So look at your QQ plots, look at your skewness and kurtosis, look at density curves or histograms to get a sense of how the data are distributed. If you do have issues with data distribution, then it's possible to transform the data in some way. So for example, you could use like a log transform or an exponential transformation. You also need to look at global trends, as we talked about earlier. So what type of global mathematical model would best describe the data? A linear model, a polynomial model, second order, third order, so on and so forth. What does the semi-variogram tell you about spatial autocorrelation? So where is the sill? Where is the range? What is there any directional trends in the data? So should you consider anisotropy? And again, this probably shouldn't say this, but I feel like this is as much an art as it is a science. There's a lot of playing with the data and looking at these graphs to get a sense of how best you can improve them. So it's a lot of back and forth. It's not just push some buttons and run a model. Okay, so things to consider. An analysis of your data will allow you to make decisions relating to, one, if data transformations should be applied. So whether you want to square them or exponential or log transform, the best function to fit the global trends, linear, square, cube, whatever. If there's any directional trends in the data to modeling the local trends. From that, you can define a best search direction and width to understand that directionality, and then by looking at the semivariogram, you can specify sill, range, and nugget to again model local spatial variability and spatial autocorrelation. One thing nice about the Kriging surface is that because you have an estimate of the known values, you can also estimate uncertainty. So here we have a prediction. So this is different ozone levels across California, and this represents error rates. So here we're seeing lower error rates closer to the measurements, as you'd expect, and increasing error measurements as you go further away from the measurements. Again, more extrapolation, less control over the analysis. Okay, and just as a couple final notes, if you want to implement Kriging inside of ArcGIS Pro, the best way to do it is generally using the Geostatistical wizard. So again, it's not foolproof, and you have to do a lot. You have to understand what you're doing, but this does step you through a lot of the processes that you need to undertake in order to perform Kriging. And as you can see here, there are other methods that are available, such as inverse distance weighting and polynomial interpolation. So this isn't just a Kriging tool, but it's very useful to undertake Kriging. And then as a final note, there's different types of Kriging. I did want to mention the concept of Co-Kriging. So sometimes you'll have a variable that's, say, correlated with your variable, the variable you're trying to predict, that they could potentially improve the model if it's included. So for example, if you were trying to predict say temperature, incorporating say elevation into the model could be useful. So basically Co-Kriging is where you add a covariate, so like an X or an independent variable or predictor variable that may help improve the prediction. So you're not just making use of your point measurements and the global trends and the local spatial autocorrelation, you're also making use of a covariate that could potentially improve the model. So for example, temperature predictions may be improved by incorporating elevation. Okay, so that's a pretty short introduction. Again, this is a pretty complicated topic, and here I just want to get you thinking about what spatial interpolation is, some different methods that we use, pros and cons with different methods, and then in lab you'll actually implement some spline and Kriging and Thiessen polygon type surfaces. We won't be doing Kriging in the lab, but it's something that I think you should at least be aware of, because if you take more advanced courses, you'll probably run into it in the future. Okay, thanks.